remind everyone again at the end of the lecture, but in case I forget, tomorrow you should be here at 9:45, just to get in and settle in and so on. Okay? But I'll say a few words at the very end of the lecture, and it's a pleasure to have the very last lecture by Chong.
Okay. Well, normally, if this is the last lecture of the school, I would assume you're looking forward to the end of it, but then I realized I'm the only thing standing in between you and your exam. So I don't know if you should be looking forward to it or don't want this to go. All right, so before we start, any question about yesterday? Let me actually first remind you what we did yesterday very briefly. So we're talking about, well, mainly the toric code. So it's a 2D lattice. What about this? Okay. So you have your qubits living on the edges, and the Hamiltonians consist of the vertex term and the plaquette term. They look like this. The important thing is they all commute with each other. So solving for the ground state really just means each one of them acts on your ground state as, the ground state is eigenstate of each one of them with eigenvalue +1. Okay? We're working with periodic boundary condition in both directions. So our space is topologically a torus. And on torus, we spend quite a lot of time figuring out that the ground state is fourfold degenerate. And we can figure out the operators that act within this fourfold degenerate subspace. Essentially, you have fourfold degeneracy that behaves like two independent qubits. These are the effective Pauli operators acting on the two qubits. Right? They are Pauli operator because they have this anti-commutation rule like this. And the important thing here is that these are loop operators. Right? So they don't act locally. They act on an entire loop. In fact, they act on the non-contractible loop, the topologically non-trivial loop on the torus. Right? So there are two such loops on the torus. Right? One we call CX, which is a loop that transfers through the x direction that wraps around your torus like this. The other one is CY, which is a loop transversing along the y direction, which on the torus is like this loop. Okay? Yes? Yeah, that's one thing I probably glossed through quite quickly last time. So this I put a prime here to differentiate from this notation because strictly on the lattice, these two loops don't literally live at the same place. So for that CX, what I mean, the loop looks like this. Right, literally on every link along this loop, you put a sigma Z operator. So this is my CX. Now C prime X means something like this. So you draw a loop like this that instead of living on the edges, it goes through the edges, and every edge it goes through, meaning every edge it intersects. So here for this one you put a bunch of sigma SZ, but here you put a bunch of sigma X. Right, so this we call CX prime. The more precise way of saying that is CX prime is a loop living on the dual lattice instead of the original lattice. Dual lattice means you treat the center of the face of these plaquettes as vertices, and then you connect them together. You realize that that's another square lattice. And now this C prime link lives on this dual lattice. Right? But that's more like a notation convenience. It's not super essential. Okay. Any other question? All right. So last time, I kept saying that really important thing is this effective Pauli algebra, this non-trivial commutation generated by loop operators that wraps around your space. Essentially, everything cool about toric code is really a consequence of this kind of loop operator algebra. Okay. Particularly one thing I showed you last time, well, more or less showed you, is that one consequence of this is that this fourfold degenerate ground states, they're all locally indistinguishable. Right? If you look at any subsystem that has a topology of a disk, meaning it doesn't cover a large loop of your torus, then you take any state within this fourfold degenerate ground state subspace, the reduced density matrix look identical on this, which operationally that means you measure the expectation value of any operator that acts only within this region A, you get identical results. Okay. So that's one consequence of this loop operator algebra. Let me show you another consequence now. Okay. So this is a consequence about excitations, right? I've been focusing almost exclusively on the ground states, but let's also think about the excitations. Right? It turns out for that purpose, these are all like operators living on closed loops, and another important thing is these operators they behave as symmetries of your theory, right? In particular, namely, they all commute with this Hamiltonian, right? But now let's do something slightly more violent. We open up the loop operators. A string operator. So what do I mean by that? Well, for example, instead of a bunch of sigma z living on a closed string, let me draw an open string like this, right? With two endpoints, right? With sigma z, sigma z. Right, now this violates the rule I explained from last time. So you don't expect this operator to behave as nicely as the other operators. Right? It's not a closed loop. It has two endpoints now. So let me call this operator. Let me call this string L. Right. So this is an open string L. And then let me define this ZL as the product of all the sigma z's living on this ZL. Okay, so this is no longer a symmetry. Right. By that I mean it does not commute with the Hamiltonian anymore. But the non-commutation, if you stare at this, is actually quite mild, right? Because, okay, so which term could it possibly not commute? Well, that's a bunch of sigma z, so it's definitely commute with this BP, which is also a bunch of sigma z. The only thing you need to worry about is this vertex term, which has a bunch of sigma x, right? Sigma z and sigma x anti-commute, so there's a potential source of minus sign when you try to commute these things. But of course, to actually have that minus sign, you want that open string and this vertex, the four edges from the vertex, to overlap an odd number of times, right? In order to have that minus sign anti-commutation. So, so basically, so this guy only anti-commute with AV and AV prime, where V and V prime are the two endpoints of my open string, right? Because away from this endpoints, if you're here, you can't tell if the string is open or closed, or a closed loop, right? Because you look at this vertex, it overlaps with the vertex twice, right? So it's only at the endpoint where you overlap with the vertex term only 3 times. Sorry, only odd number of times. Right, is that clear? So V and V prime are the endpoints. Also, you notice that by very similar reasoning as we explained yesterday, the actual shape of this open string doesn't really matter, in the sense that if I start from an open string that looks like this, I can use a BP term, right? The BP term is a multiplication of a bunch of sigma z on a closed surface, on a plaquette. So you can multiply by a BP term and convert this line into this shape. So what you have done by doing that is to deform the shape of this line, right? So you know the fact that it's straight or maybe it curves around for a few times, it doesn't really matter, right? What does matter is here's an endpoint, here's another endpoint. That fact will not change by just hitting it with BP. Okay. So for this reason, we'll just label this loop by the two endpoints. Let's just call them V and V prime. Right. Actually, maybe V1, V2 is better. Yeah. Okay. V1, V2. Okay. Any question about that? So what does this mean? Well, it means that if I start from a ground state, right? Let's say any ground state, and I act with this string operator with the two endpoints V1, V2, right? It's no longer a ground state, right? Because this operator anti-commutes with some of this, with this V1 and AV2, which means now this new state has the eigenvalue of AV1 and AV2 being -1 instead of +1. But every other term is fine, right? Because this term commutes with every other term. So so this is an excited state. But it's a very low-lying excitation, right? So with in fact, you only have two of the A terms being unhappy. Each unhappy one gives you an excitation energy of 2. So this gives you an excitation energy of 4. So this excited state, so the energy is 4. Sorry. The important thing is you should view this as two, let's call it A excitation at V1 and V2. By A excitation, I just mean a vertex where the A term is -1 instead of +1, right? Just so it feels like two particles, right? So two particles, right? By particle, I mean a point-like excitation, right? Because it's point-like. Only a single AV term localized around the a point V is excited. So let me just call it the A type of particle, right? Yes. Yeah. So the statement is that this Z, let me just for now call it ZL, right? I don't want to keep writing V1, V2. A V1 equal to minus A V1 ZL. That's fine, right? So now the statement is originally AV1 ground state. Well, that's an eigenstate with eigenvalue +1. But now let me think about AV1 acting on this new state. Well, let me take off the bracket. Doesn't really matter. And then let me switch this to. Well, when I switch this to, I get a minus AV1 ground state, but by this line, this AV1 is canceled. So what that tells me is that ZL hitting on this, sorry, AV1 hitting on this new state gets just this state itself, but now with eigenvalue -1. Right? Yeah, that's the trick you always use whenever you have some commutation that looks like this. Oh, yeah. Because remember, the Hamiltonian is the sum of a bunch of these terms, right? Yeah. Yeah. Very good, very good. So, so you can ask, well, as I explained last time, an excitation means some AV or BP is unhappy, right? So some of them become eigenvalue -1. Now I have two of this here. You can say, okay, maybe an even lower one would be just one of them being -1. But on torus, remember we have this this relation, which is the product of all the AV terms, all the vertex terms, is actually not a new operator, it's just identity. Which means every time you try to flip the eigenvalue of AV, you have to flip even number of them. Right? So this turns out to be the minimum energy excitation. So this tells you that this guy is actually the lowest excitation. On torus. Yeah. Sorry. Oh, the reason is that this to be a symmetry, you want, for example, these things are good symmetries because they commute with every single vertex and plaquette term. So and therefore it commute with the Hamiltonian. Now to ask if a new operator like this is a symmetry, you just ask the same question: Does it commute with all the AV and all the BP? And then you realize that for the AV, the V at the end of this string, it no longer commutes, right? Because there you have a sigma Z here. Remember AV is like sigma x, sigma x, sigma x, sigma x. So here you have a sigma x that anti-commutes with the sigma Z. Sorry, why do I have it twice? So the AV1 will be, sorry? Oh, sorry. Here's a comma here. It's not product. It anti-commutes with AV1 and it anti-commutes with AV2. Right? Yeah. Any more questions? Okay, good. So you get the two-particle excitation, right? So each part. So let me. So what I mean is, what I want to say is each of this A excitation, for example, the A excitation at vertex V1 behaves like a particle. Well, there are two key properties of what we normally call a particle. One, it carries energy, in which case it does. Right? It's literally where this AV term gives you an energy excitation 2, excitation energy 2. The other thing is a particle should be able to move around. Right? So it turns out we can move this particle around. So we can move it around, let's say from, for example, V1 to, let me call it V1 prime, through a loop operator. Actually, using the same kind of loop operator that gives you from V1 prime. What do I mean by that? Well, let's say I have a string operator acted on the ground state, so I create two excitations. Let's say I have V2 and V1. And now I say I want to do something to the system, aka apply some unitary operator that moves a particle from this location to a different location. Let me call it V1 prime. Right? How do I do that? Well, I do that by applying this Z V1 V1 prime. What do I get? Well, I get here V2 V1. Well, prime, I get something like this. Right? Do you see what I'm doing? So once I act on this state further with this Z V1 V1 prime, the whole thing becomes just a longer string operator, starting from V2 ends at V1 prime. So now I have started with a configuration with V2 excitation, V1 excitation. Now I have V2 excitation and V1 prime excitation. So what I have been doing is to move the particle from V1 to V1 prime. Right, so I have a kind of operators that move these particles around. So they really look like, well, what we normally call particles, like your electrons or something. Okay? In many ways, right? Not in every way, but. Okay. So I've been using this Z loop operators, but you can, repeat the game with exactly the same logic for the X loop operators. So you can similarly an open string. Let me call it XL prime. Let's go from P1 to P2. So let me just draw it. Right. So I'm thinking of having an open loop operator where it starts, now it has an endpoint. It starts from P1, ends at P2. Right? Which is a product of spins living on this L prime, P1, P2, sigma x on side I. Right? So it's, again, it looks very, very much similar to that one. This one, instead of the older one commuting with, not anti-commuting with AV at the vertex term at the endpoints, this one is anti-commute with BP1, BP2, where P1, P2 are the endpoints of this dual string. Okay. So I'll call them the B excitations, right, for obvious reason. Okay. Any question about that? Okay, so okay, you get some particle-like excitation, right? You say big deal. What's the deal, right? So there is a very interesting phenomenon here that I can immediately tell you, which is now imagine moving an A particle, an A-type excitation, around a B-type excitation. Right? What does that mean? Well, it means that let's imagine I have some kind of B excitation. Let's say some BP here equal to -1 with a string attached to it. Maybe maybe somewhere far away you have another B type of excitation. Let's not worry about that one. And now I have another particle which is like this AV equal to -1. It's also attached to another string. Maybe far away there's another A excitation. Let's also not worry about that. So now I try to move this particle around this particle, right? But as the rule I just listed, when I say I move a particle around another particle, what I'm really thinking about is to apply a unitary operator that lives on a string, right? So then I can apply an operator that moves it from here to here, and then from here to here, and then eventually around this BP particle. But then eventually, let me bring the particle back to the original position. Right? So I can do that. So it looks like I go from a state. Let me just label the original state as you have a BP particle. You have a B type of particle at P and A type of particle at V schematically. Now I apply this closed loop operator. What I'm doing is to move this particle around the other particle, right? So that's a particle that's called, I think that's a Z particle that moves me around this closed loop. Well, at the end of the day, this particle goes back to the original position. So naively you say, okay, it's the original state. So you may want to say that I'm just going back to my original, B particle at P, A particle at V. It's the same state. However, notice that this is a Z particle, a Z loop operator. And to create this BP, I need an X operator here. These two anti-commute with each other. So when I apply this ZL operator, I actually get a minus sign. Okay, it's the same minus sign that we keep seeing, right? Because for the same reason, whenever this loop and this loop intersect once, you get a minus sign. Okay. So the statement is that, so the important thing is this L prime intersects once. And by the way, this is a robust statement, right? When I define the particle here, I could have drawn the other loop in a different way, and this operator that I use to move the particle around, it doesn't have to look like this. It can look like this, but it doesn't really matter as long as I'm moving one particle around the other and return to the same position. These two loops have to intersect an odd number of times. Right? That's what matters, and for that reason, you get this minus sign. So this is actually a robust statement. Right? So basically, moving this A particle around B particle gets you so your wave function gets a -1 sign. Okay. So the jargon sometimes people use is to say that this A particle, so this A particle sees the B particle as a pi flux. Right? So pi flux really means e to the I pi is -1. So that's well, the reason for using this this kind of wording is to remind you about electromagnetism. Right? So if I think about quantum mechanically, moving a particle around a magnetic field. Let's say you have some magnetic field like this, and now you move a particle around this magnetic flux. You pick up a phase. Right? So that's the famous Aharonov-Bohm phase, which is e to the I q and the loop integral of your gauge connection along the loop, which also happens to be e to the I q times the magnetic flux penetrating this loop that your particle moves around. Right? And this phase is very much mimicking that. And in fact, the analogy can go deeper. I won't say much about it, but secretly, what I've been teaching you for these 2 days is a gauge theory. Right? Except it's not the usual E&M gauge theory where the gauge group is U1. This one gauge group is Z2, so everything is just plus minus 1. Right? And the statement that particles can be created only in pairs, not on its own, is actually an analog of gauge charge conservation. So everything actually has a very close analogy to E&M. But I'm not going to say too much more about that. I'm not assuming a background in quantum field theory. So let's not say too much about that. Okay. Yeah, but feel free to ask anything. You know, if it's okay. So okay, you say okay, I have two different particles. They see each other. There's some funny phase factor of pi when I do something funny. Okay, still, what's the big deal? Now let me tell you something that looks really weird. If you know, it's a direct consequence of that. That looks really weird, and really fun. So I think I don't need this one. It looks really fun when you bind an A particle to a B particle and ask what's going on. Right? So fun consequence. So now let's bind an A particle to a B particle. Okay? So the claim is that this AB bound state, this combined object, is a fermion. Which, if you really think about it, is quite remarkable because fundamentally we're having a bosonic system. So by bosonic system, what I mean is operators at far away locations, they just commute. Right? We're having a bunch of Pauli spins. Right? That's everything on different sites, they trivially commute. Right? Things that commute means that when you try to exchange the order, there's no funny phase factor coming up, right? So the system is fundamentally a bosonic system, right? There's no exchange phase, anything. But through this collective interaction and this collective behavior, you end up with some excitation that behaves like a fermion, right? So this kind of behavior is so sometimes we say that this is a fermion. This is when the fermions emerge out of bosons. Right? Emerge means microscopically they're not there. Right? You take a bunch of Pauli operators, they never, for different spins, they never anticommute. But when you go to low energy, these excitations behave as if they're basically particles with fermion statistics. Okay. So let me give you two justifications, a cartoon justification and a serious justification. But let's see how much time I actually have for the serious one. But at least let me show you the cartoon, right? So this is, by cartoon, I mean it doesn't look rigorous. So if you are very careful, you can poke a lot of holes in this argument. But it turns out to be more or less correct. So just bear with me for a little while, right? So let me just pictorially think about what I mean by A bind to B, right? What I really mean is let me put an A particle here, let me put a B particle here, and then I say, okay, they're at different location, but let's say I bind them together so that they don't get too far separated. On the lattice, you can literally draw this, right? Because on the lattice, an A excitation looks like this, and a B excitation looks like this. So you can literally put the two strings side by side, and then at the endpoints, you do get this combination of A and B, right? So in case you think things look abstract, just literally put it on the square lattice, right? Put the two strings side by side. Everything I said will be applicable. Okay? But now let me just draw the cartoon. Let's not worry about details of how they look on the lattice. Right, so you have a particle put side by side to a B particle. Well, we just said that if I move the A particle around B particle, you get a phase of pi, right? So, which means if I take this, if I think of this as some kind of dipole, right? I draw an arrow from, let's say, B to A, right? Then this statement means that if I rotate this arrow by 2 pi, I get a phase factor of pi, right? So if I, rotate this by 2 pi, I get a phase factor of -1. Now, recall your undergrad quantum mechanics class, when you learn about angular momentum. What does that mean? Well, it means that the angular momentum let me call it J, is a half integer. It's not an integer. It's n plus 1/2. Because if it's an integer, then under 2 pi rotation, you're not supposed to get any phase. It's only when it's half integer, then under 2 pi rotation, you get a -1. But there famously is, yes? Because this arrow means the arrow from B to A. So this arrow rotating by 2 pi just means I'm taking A around B for a full circle. But this story tells me doing that will give me a factor of -1. Yeah. So you get a half integer angular momentum, and famously, half integer quantum angular momentum means fermion statistics. Okay. Any question about that? Right. If you feel this argument is somewhat weird, you're on the right track because I'm doing something slightly illegal. Actually, it might be a fun exercise for you to think through exactly where things are illegal. But for one thing, this connection between angular momentum and boson versus fermion statistics is better justified if I have a relativistic Lorentz invariant theory. Here I'm on a lattice. What do I mean by Lorentz invariant? I don't even have continuous rotation symmetry. What do I mean by angular momentum when I don't have continuous rotation symmetry? Right? So this argument is full of holes you can poke. But at the end of the day, it's actually correct. So, okay. Let me see. Do I need? Yeah, I think I don't. Yeah, let me erase this part. So, yeah, I think we have time for the more serious justification. So that, when I say so now let me tell you a more serious way to justify this. This is not so much to tell you about the details of various things. There are many details we can go into. I'm not going to do that. But the point is to give you a flavor, show you a flavor of how people make arguments or define things. in this field, right? Yeah, so in case you think this part is too formal, just think about that. It's fine. It's basically enough. Okay. So the more serious, if you think about this a little bit more seriously, the first thing you realize you need to clarify is what I mean by statistics. What do I mean when I say a particle is a boson and another particle is a fermion, whatever, right? So particle statistics, meaning boson or fermion, especially when you don't have things like Lorentz invariance and so on, is really a property of the operators that move the particles around. Right? Because what I mean by having a phase, you're thinking about a process where you change two particles. Right? And by the end of that exchange process, you get a minus sign. But in our case, these operators are the string operators. So what I'm saying is that the statistics of the particles should be encoded in the properties of the strings. So let's call this string operator just, let's say, from point 1 to point 2. Let's just call it S1, 2. Right? Just, if it could be our ZL or, XL prime, or the combination of the two. Right? So here's one way to define statistics. Turns out that's that statistics. Here's a definition, one way of defining. There are more than one way to define. Yes? Sorry, by combination, I mean you just take the product. You just put them side by side, take the product. Sorry. What I mean is something like this, right? You put a bunch of Z's here and a bunch of X here. Yeah. And you call this point 1, this point 2. Yeah. Right. Yeah, I mean, practically you just need the distance to be finite. But on the lattice, it's convenient to literally put them together.
But I can only use that structure.
Yeah, it turns out it doesn't really matter. Even if you put the other string here, as long as this distance doesn't become too large, it's fine. It turns out what I'm gonna say doesn't care about that kind of detail. It better not, right? Because otherwise it depend on too much detail and it's not fun. So here's how I define statistics. You think about a string operator that take you from between point 1 and 2, and then immediately followed by 3. So let's think about this as 1, 2, 3. Right. So think about this as this is doing is to take particle from point 1 to point 2, and then to point 3. Right. Some simple thing. And then think about another string operator that takes you from point 1 through the same string. I mean, they're really the same position. I'm just drawing it so that you know what I'm doing. But these are really the same loop to point 2, but then to point 4. Okay. So what am I doing? So I'm first taking a particle from point 1 to point 2, and then to point 3, and then taking a particle from point 1 to point 2 to point 4. Oh, sorry. This way of writing it, I'm doing actually the opposite order. Let me just say this. right? Because you read the operator from right to left. So you first take 1 to 3 to 4, and then to take another one from 1 to 2 to 4. Okay? That way, you end up with 2 excitations, one at 3, another at 4. But you can do it in the opposite order, right? There's an opposite order, which is S1, 2, 3, followed by S1, 2, 4. Means I take this particle to 4, one particle to 4 first, and then a particle to 3. Both ways, you end up with one particle at 3, one particle at 4, but you did it in opposite order. So if it's fermion, there should be, or in general, there should be a phase factor associated with this ordering, right? If you are doing the opposite order, you get the same state, but you expect a difference as a phase factor, right? And if it's +1, you call this particle boson. If it's -1, you call this particle fermion, right? So that's one way. It turns out, I mean, I'm not going to explain that, but it turns out this definition is actually a pretty nice one in the sense that there's sometimes some ambiguity of exactly how you define the string operator and so on. But turns out this definition is robust against all those ambiguity. But that's some technical remark. You don't need to worry about that. So this one is what I call statistics. Now you can literally very explicitly verify what is this phase factor for this AB combined particle. It's actually a quite simple calculation once you've set up things properly. So, so for this AB combination, right? Actually, I've already drawn the string operator here, but let me draw it schematically as just putting 2 strings side by side. One is a Z, another is an X. Okay, so this solid line, this a Z string, this dashed line is an X string. Okay. So what are these objects? So this 1, 2, 3 is something like this. Right? I'm just literally putting the 2 side by side and bend it so that it looks like this. And now let me try to draw 1, 2, 4. It's like this. Right? I'm not doing anything crazy. Now, put this 1 on top of 1, 2 on top of 2. You'll see the magic. Just this 1, 2, 3. I have this one. Right? Now, if I want to draw 1, 2, 4, I instead have this. Let me know if you don't see what I'm doing. It's I'm literally just stacking this figure on top of this figure. Right? But then you notice that this solid line and the dashed line intersect exactly once. And remember, our rule of game is that because the solid line is a bunch of poly Z operator and the dashed line is a bunch of poly X operator, when they intersect, it means an anti-commutation relation. There's a minus sign in the commutation. Right? And you can see just by staring at this figure that this is the only place that this kind of intersection happens. Takes a little bit more work for you to see that doesn't matter how exactly you arrange the position of various things, you always end up with odd number of such intersection. So this guy is minus sign. So you do get a fermion. Right? So that's the serious justification of the fermion statistics. Okay. If this cartoon doesn't convince you, since we have explicitly the form of the string operators, you can do an exercise which is literally draw this properly on the square lattice, draw such figures on the square lattice, and then you'll see that indeed you get an intersection, you get exactly one link where the sigma x and sigma x and sigma z have to interchange order, so you get a minus sign. Okay. Any question about that? Okay. All right. So that's all I want to say about excitations. Now I'm going to go back to the ground state business. Yeah. No, I'll just let things sink in a little bit. You know, if it's first time for you to see it, it's a pretty bizarre thing. Take some time to sink in. So next, I want to finish this series of lectures by discussing something that I've been promising to do. Maybe not fully, but at least give you a glimpse of. So it's about the issue of stability. Right? Because so far, I've told you a bunch of examples that are very carefully designed, right, almost ingeniously designed, to be solvable. Right? Every operator commute with every other operator. So if you want to figure out the ground state, it's a rather straightforward task. You just let them to be all one. Right? Generically, you never have that. Right? You perturb this Hamiltonian with pretty much any term you can imagine. Even if the coefficient of those perturbations may be small, you immediately lose this property of everybody commuting with everybody else, and you lose solvability. And in general, it's going to be a exponentially hard, in terms of computational complexity, it's a hard task to figure out exactly what the ground state looks like, what its detailed property, and so on. So, so a very legitimate question is how much do all these things that I've been spending time telling you about still survive, right? Even if I add a little bit of perturbation. Right? The fact that I've been spending so much time telling you this presumably is a hint that these things still mean something, even in those unsolvable limits. And that's one thing that I'm gonna show you. Okay. So specifically, let's ask how stable is toric code's fourfold degeneracy on torus. For example, on the first lecture, I showed you that the Ising model also has a twofold degenerate ground state. But if I add a generic perturbation that breaks the symmetry, that degeneracy is gone immediately. Right? Even if I add an infinitesimal such perturbation, you don't have such degeneracy anymore. So a legitimate worry is whether you have similar problem for the fourfold ground state degeneracy for toric code. Right? If you do, then this is a lot less interesting. It turns out this is stable, but and you already have enough information to show that. Right? So let's think about a perturbation, just to be concrete, with some coefficient lambda that's much smaller than 1. And it says the Hamiltonian is a sum of local terms. So each delta I is a local term that acts non-trivially only within a finite distance away from site I, and lambda is much smaller than 1. Right? Other than that, I don't really impose anything. Right? This delta H can be, I don't know, involving 10 spins with weird combinations of the spin operators. Doesn't really matter. Okay. So the strategy, whenever you see some funny-looking degeneracy of ground state, actually for any state, but let's particularly specifically talk about ground state. When you try to analyze the stability, you use degenerate perturbation theory. right? So it's not something super fancy. It's just basic quantum mechanics. Okay? Let's do it. Let's first do the simplest thing, which is first order, right? Which is really simple. So in first order, degenerate perturbation theory is really just a fancy name of saying neglect all other energy levels, just look at this fourfold degenerate states and pretend your Hamiltonian only act within this fourfold degenerate subspace and look at what that does. So the only thing you need to look at, let's just say you have psi A and psi B. Let's say they are orthogonal. That doesn't really matter within this ground state subspace. Okay. Or let's say A B is labeled by an orthogonal index, a complete basis index. Okay. So to first order, what you need to look at is the effective matrix element of this perturbation in this degenerate subspace. Okay, so let's say AB runs over 4 indices because it's fourfold degenerate. So this is now a 4x4 matrix. So in degenerate perturbation theory, what you do is to diagonalize this fourfold, this 4x4 matrix, and then you get whatever ground state you get is your new ground state after perturbation. But what does this look like? Well, this looks like lambda sum over I, psi A, delta HI, psi B. Right? And then, remember, you have the important result we discussed by the end of yesterday, which is local indistinguishability. Which means if I'm only allowed to use a local operator to probe the ground states, then all the ground states look the same. There's absolutely no way for me to tell one from the other. Now, this is a local operator by assumption. So it satisfies that rule, which means this guy should be proportional to delta AB. Right? It means the expectation value is the same for all the ground states, for all states in the ground state manifold. Furthermore, the off-diagonal terms are all 0. Because if the off-diagonal term is not 0, you can rediagonalize the Hamiltonian, and then you get like you can differentiate the new states. Right? So the only way this is compatible with local indistinguishability is that the effect of this perturbation looks like an identity operator on the ground state manifold. Right? The coefficient of that identity could be, in general, it could be proportional to volume and so on. It doesn't really matter. But the important thing is that fourfold degeneracy stays robust. So doesn't lift this fourfold ground state degeneracy. Okay, so that's already the first sign that this degeneracy may be robust. Okay, that's a first sign. But okay, if I only stop there, you can complain. This is first order. That's a little bit too lame to just do it. So let's think about higher order. Right? So let's think about nth order. Right. Now, yes. Yeah. Essentially, what I'm saying is that this should be an identity operator, because if it's not, it means the eigenvalues are not completely the same. Right? Some will have eigenvalue plus something, some will have eigenvalue minus something. But in that way, but if that's the case, that means I can distinguish different states within this ground state manifold by measuring the expectation value of this operator, which violates local indistinguishability. Yeah. Okay. So let's go to higher order. I say nth order because the logic will be the same for second order versus 100th order. Now, so to nth order, you basically have a very similar matrix. Right? It's again some matrix that act, you take some operator and take matrix elements in between, except that operator looks more complicated. Right? So what does that operator look like? Well, that operator looks like some combinatorial factors, which you spend a lot of effort getting them correct in your quantum mechanics homework, but here I don't care, right? Some number. And then to take the matrix element, you take delta H to the power n. And B, right? Okay, that's not really the end of the story because you see that the dimension doesn't work out well. This is energy to the nth power. So this is, it comes with some denominators, right? So for example, if you do second order perturbation, the denominator will be something like E1 minus E0. You think of it as the energy first takes you from ground state to some excited state and then eventually come back to ground state. That's the process we're talking about, right? And if it's nth order, there's many, roughly speaking, it's some n minus 1th power. But the important thing is, we also know that the gap is finite, right? So this E1 minus E0 is at least something like 4 or something, right? The important thing is it's just a finite number. So again, this is just some finite number that goes into that number, which I don't care to work out anyway. So let's not worry about that. So yeah, let me be a little bit more careful. So this is some energy scale that's at least greater than the gap to the n minus 1th power, which is some finite thing. Right? So now, what does this mean? Well, this is now up to just some number times lambda to the n. Lambda is the coefficient of this perturbation. Now I'm in the nth power. And now let me just expand this sum, right? So delta H is a sum over local term, and I raise it to nth power. Let me just expand it. Well, what does it look like? Well, it looks like psi A, delta H I1, delta H I2, blah, 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 delta H IN, psi B. Now I get a more complicated object like this. What does that look like? Well, it means that I'm summing over all kinds of locations with n of them. Let's say if I'm in the 4th order, then I'm looking at a figure like this, right? So this is my I1, I2, I3, I4. But still, in this kind of situation, all these i's still live in a disk-like region, right? And this region doesn't contain any large loop, any non-contractible loop. So by the same local indistinguishability we've been talking about yesterday, exactly the same result applies. Yes? I1 means position 1. It can be, eventually you're going to sum over I1, I2, I3. Right. No. I'm saying this points formed by I1, I2, I3, I4, you can draw a circle and realize that they all belong to this circle. And this circle is a disk. Topologically, it's a disk. So as we discussed yesterday, as long as your region looks like a disk, you have local indistinguishability. Even a messy operator like this will not be able to tell different ground states apart. Right? Yes?
But what if we have the points arranged? Like
Hold on. You're on the right track, but hold on. So, which means this guy is, again, proportional to delta AB, and in particular does not lift my degeneracy unless n is of order L. Right? If n is of order L, as correctly pointed out, now you can have a situation where my eyes arrange like this. Right? For example, I can have a situation where all this delta H, they take, when you take the product, it basically becomes one of these guys. And then you can, these guys act non-trivially on the ground state manifold, so they definitely can tell the different ground states apart. Right? But this is a very high order. If I have a large system, right, you have to go to some ridiculously large order. And remember, you have this factor and the assumption that lambda is small, which means there's a correction to this identity operator, but the correction is of order lambda to the power L. Right? And this correction, in principle, okay, they can lift the degeneracy. They can create some splitting of the degenerate manifold. But then you conclude that the splitting of the 4 degenerate ground states is exponentially small in system size. Goes as e to the minus L over some length scale. Sometimes we call this length scale Xi correlation length. Right? And this is just another way of writing lambda to the power L. So I lied to you a little bit. Right? This fourfold degeneracy is not exact at the end of the day, but it's really damn good. Right? Exponentially small in system size is practically, you won't be able to tell. Right? Think about it, a size of 100 by 100. Right? So the picture you end up getting is that, let me draw the final picture. So the final picture is, let's say, think about turning on a perturbation. Let's call it lambda. When lambda is 0, you have your solvable point where you can figure out all the energy levels exactly. You have an exact fourfold degeneracy. And then there's some excited states, right, with some finite energy gap. Once you turn on this lambda, what you find is that things basically evolve continuously. But here, you do get a little bit of splitting. But this splitting is absolutely tiny. So you can basically neglect them. And then whatever excited states you have up here. Right? So this structure of 4 degenerate ground state with a finite gap for the next excitation, that remains. Right? And whenever this kind of continuity holds, so this kind of continuity is sometimes called adiabatic continuity. So if I have 2 Hamiltonians, 2 local Hamiltonians, they can be interpolated through such a kind of adiabatically continuous path through some adiabatic continuation. They are said to belong to the same phase. This is actually one way to actually carefully define what I mean by phase. I've been saying that this lecture series title is quantum, topological quantum phases. this is the proper definition. And this relies on the stability of the structure under perturbation. Okay. By the way, there's also a side. You can also use very similar argument to show the following. Let's go back to the Ising model case. Recall that for the Ising model, this twofold degeneracy is not stable, right? So if you break the symmetry, turns out this, you only get a unique ground state. But it turns out, if this perturbation, right? So if I have a perturbation where the perturbation itself does not break the symmetry, where this local term commutes with the symmetry operator. So remember, X is the product of Pauli X operator for all the spins. Then you can use exactly the same argument here. It's a fun exercise for you to try. To show that this twofold ground state split, again, only by a splitting that's exponentially small in system size, in the volume. So D is the dimension of your space. Right? So there, even though if you break the symmetry, this feature of twofold degeneracy is not stable. If you keep the symmetry, it turns out it is stable. It is very much stable. Yeah, you can show this with exactly the same type of argument. Okay. And finally, let me just tell you some fact. I mean, let me just tell you some fact about the fate of this operator, right? So I just showed you that this fourfold degeneracy is, sorry, go ahead. Yeah, for the Ising model, yes. Yeah, for the toric code, it's just L. Yeah, it turns out in any dimension for the toric code, it's just L. But yeah, for some deep reason, but yeah, go ahead.
Why is it exponential?
Sorry?
Why is it exponential?
Why is this exponential?
Why exponentially? Why we turn this exponential with L?
Oh, because it's this. Yeah, I'm just rewriting lambda as, yeah. And okay, there could be some combinatorial factor, but I'm also absorbing them. Yeah.
And why do we mean exactly by H1 equivalent to H2?
Yeah. What I mean is you can get from H1 to H2 through a continuous interpolation like this, where everywhere in between, your gap remains finite, your ground state degeneracy remains the same up to potentially exponential correction, exponentially small correction, right? If such a path exists, I say these two belong to the same phase. They are basically in the same equivalence class in some sense. Yeah, go ahead. Oh, yeah, sorry. What I mean is imagine two different Hamiltonians, right? And then if there exists a path, a kind of, from one Hamiltonian, turn on some perturbation, maybe reduce some term gradually. Yeah. For example, this picture, what this picture shows you is that this toric code Hamiltonian and the totally trivial, just sigma x Hamiltonian cannot be connected this way, right? Because one has a unique ground state, another is supposed to have a stable fourfold degeneracy. If you really try to interpolate between, something funny must happen in between, right? the gap probably closes or something like that. All right. So yeah. So I have I showed you that this structure of the four-dimensional, four degenerate ground state subspace is robust. And then it's very natural to guess that, okay, it sounds like you have some structure like 2 qubits, right? 4 degenerate ground state, that's like 2 qubits. So this 2-qubit structure is stable. Therefore, operators acting on this 2 qubits should somehow be robust as well, right? I mean, when you have a 2-dimensional Hilbert space, 4-dimensional Hilbert space, you should have some operator acting on them, right? In some interesting way. It turns out to make that precise takes a lot more work, a lot more than just doing this. So I'll just tell you the result. Right. So remember we said this fourfold ground state degeneracy is stable against small perturbation. And so it turns out, when I say it turns out, I mean I'm just going to tell you the fact. I'm not going to tell you why it's true, because this needs a lot more work, actually. Turns out, when you have this kind of adiabatic continuity, I'm just repeating the figure there. So you have your fourfold degeneracy up to some exponentially small splitting, and your ground state like this with the gap kept open throughout. When this is true, here, when you are undeformed, this ideal toric code, you have the string operators x12, z12, right? Where they, it's basically a bunch of products of sigma x, sigma z, satisfying this Pauli algebras. They live on the strings and so on. It turns out, in this deformed theory, this much more general theory, you still have an analog of this x12 and z12. So let me call them now the x tilde 12 and z tilde 12. Turns out these guys, so this x tilde, z tilde, they are no longer as simple as a bunch of Pauli operators. Sigma x, sigma z. In fact, the exact form of this is of them generically is very complicated. It's actually very hard to write down explicitly, but one can show that they exist. So they no longer look simple, but still they act on loops. In particular, this non-contractible CX, CY loops, right? They are still Z2. And they still satisfy the Pauli algebra. Again, the explicit form of this will look horrible, actually. I mean, too complicated to write down for it, even for a computer. But the existence of this kind of thing can be proved, actually. And basically, all these structures that we've been using remains. In particular, their consequence also remains. This fourfold degenerate ground state remains locally indistinguishable, and you can also talk about the open strings. They create excitations, And because of this non-trivial commutation relation, these excitations also have this weird -1 phase from mutual winding. And if you take the bound state of these two excitations, it still behaves like a fermion. So basically, everything I've been saying survives, right? Although in somewhat complicated form. Okay, so yeah, so that's basically the end of it. Hopefully, my original goal was to show you that this subject is fun. Hopefully, you get a glimpse of that. All right, thanks.
Questions? Very good. This microphone might be running out of battery.
So first of all, thank you very much for the lectures. They were really fun. I wanted to ask you because the KITAF paper you wrote on the blackboard as a reference of sorts.
Yeah.
Was the fault-tolerant quantum computation with anyons. So I kind of assumed we would see like some sort of connection of the toric code with non-abelian anyons. So does that show up anywhere or?
No, the toric code doesn't realize non-abelian anyons.
Okay.
Yeah, sorry. Yeah, what it has something to do with quantum information processing.
Yeah.
You can use it as, this fourfold degenerate ground state can be used as some kind of quantum memory.
Okay.
And it can also be used as an error correction. Essentially, this AV and BP, they're like the local syndromes of quantum correction.
Okay.
So there is that connection.
I see. Thank you.
Yeah.
Is there any relation between the global geometry of the, like we are on Taurus?
So sorry.
Is there any relation between the global geometry of the being on Taurus and the geometric phase we found by taking the loop of the A particle?
Oh, there is this relation because I've sort of presented in the order that because of this local anti-commutation between the string operators, you have this weird -1 phase factor. You can also present from the inverse direction, which historically people did. Just if you find you have some point-like excitations with this funny mutual pi phase, then you conclude that you have this loop operators that anti-commute with each other. And then when you're on torus, right, if you're on a sphere, they don't do much because on the sphere, every loop intersects with every other loop twice, at least. I mean, even number of times. So that phase factor never shows up. But then when you're on the torus, you can have it, these two loops intersect only once, and then they anti-commute, and then they have to span some non-trivial degenerate space. Therefore, you have at least fourfold degeneracy. So this thing, all these things are very closely related. So they really come from the same source. That's the universal source of everything. Yeah. Yeah.
Can you pass the mic in the direction?
Hi, can you repeat why you use two operators to define statistics and why it tells you if it's a fermion or a boson?
Sorry, I didn't hear the last statement.
Why the commutation of these operators tells you if you have a fermion?
Yeah. So the I already eliminated this is just one way of defining it. There are other ways of defining it. Actually, this is the way of defining things that involves the least number of strings already. So that think about this process. All right, maybe this is another way to phrase things. Think about two operators moving side by side, and then at some point I want to compare this versus this. Right? This is actually comparing the commutation between the two operators, right? And sorry. Yeah. Maybe it's helpful if you think about this direction as some sort of time. So, if I do that, and then versus doing that. I think about the particle statistics, right? This is an exchange. Yeah. Right. So everything is designed to mimic exchange, but in such a way that various ambiguities in terms of when you try to define the string operator don't come in. Yeah. That's a technical layer that I didn't explain. So if you do it too naively, for example, if you say, okay, exchange two particle, that's easy. I have two particle. I take the string operator, take this one here, take that one there. It turns out this guy has some ambiguity. Essentially, along this process, there could be some phase factor accumulated just because your energy changed along the way, right? So that's a phase factor that's going to enter, and it's not going to be very interesting phase factor, right? So you want to eliminate those kind of things. It turns out this kind of construction eliminates those. Yeah.
Sorry, I didn't understand that last part. Why you say that in the example from above you don't have that phase, that energy change?
Oh, because the energy change will be here, but it will also be here.
Mm-hmm.
It will be here, but it will also be here. So when I compare these two orders, they cancel out.
Okay.
Yeah.
Okay.
Yeah. It's basically that.
Thank you.
Can you pass the mic up? Very good.
So when we were discussing that cartoon argument to establish that the pair behaves like a fermion, you talked about angular momentum. Is there a way to define some sort of analog to it in that discrete system?
There are two answers to that. First, yes, discrete symmetries do have symmetry charge. You can call that angular momentum. It's quantized in a different rule. For example, if I only have fourfold rotation, like on the square lattice, then angular momentum is defined only in mod 4, for example. Okay? So you can still talk about various things, but it turns out there's a more serious problem there, which is that angular momentum actually really is not locked to particle statistics. You can actually write down explicit models showing that, right? So when you try to take that discrete angular momentum too seriously, actually spin statistics theorem really fails, because this is badly non-relativistic. But somehow, this cartoon argument I draw doesn't really rely on that. It doesn't even rely on you have the discrete rotation symmetry at the end of the day, right? You can imagine from that term that original Hamiltonian add some provision that even breaks the discrete rotation symmetry. Everything I said will still apply. So that's the more, and that's when you need this more serious justification. Yeah, actually, okay, depending on how much you've seen in quantum field theory, actually this kind of justification is very similar to what's called the ribbon argument in justifying spin statistics theorem in quantum field theory. Right? Essentially, you imagine your particle is the world line has this thin ribbon. Okay, I shouldn't over-explain.
Okay, thank you.
Yeah.
Can I ask something else?
Yeah.
So I wanted just to ask, you said the A particles see the B particles as a pi flux, but like for the particles of the same type, do they see each other as a zero flux, a pi flux, or
zero flux?
Zero flux.
So
Both A and B.
Yeah. So actually, another thing you can check quite straightforwardly is if you use the same definition of statistics, if you just take the A particle or just take the B particle, they are bosons. All right. That's actually you can immediately verify that, because if it's a pure A or pure B, it's a bunch of just poly X or just poly Z. Of course, everything commutes with everything else.
Makes sense.
Yeah.
Thank you.
Just behind you.
Hi. When you draw these diagrams, you had kind of like superposed the x like dotted part and the line that would be the z part. I don't really get it because you had written before that like the x just applies for like the x direction and the z part just for the y direction. So why do they kind of like walk the same path?
No. All this can be in both x and y, right? You have the cy, cx. Sorry, when I say an x string and a z string, I don't mean the direction. I mean the Pauli matrices.
Oh, okay. Okay.
Sorry,
yeah.
there's the Pauli x, z versus x and y.
Okay.
Hopefully, it's not a source of confusion because y only appears for space and z only appears for Pauli. It's the x that's confusing. So maybe I shouldn't talk about x.
Yeah, because it could be like the x, but x1 and x2 when you wrote before.
Yeah.
Okay.
So, yeah.
No, yeah, I get it now.
Yeah,
Thank you.
Yeah.
Any other questions? Let's thank Chong.
Thank you.
And you are welcome to ask a few more questions informally. And see you tomorrow at 9:45. So my advice is don't overstudy for tomorrow. There's no point. The exams are going to be quite different from the other ones. So you are just going to be tired. Try to